Hello and welcome to the BinRX Student Payload Development Program Week 16, Electronic Design and Block Diagrams. So this week we're going to learn a little bit about electricity, about electronic block design, and a little bit about how to read what's called a schematic. So first, before we start, we'll go through our usual program news, program updates. So many of you, we're so glad you could join us at the end of last term back in June to present your mission concepts. If you haven't seen the photos, hopefully your teachers have shared those with you because there were some fabulous ones. And we had a great time. Our team had a great time. We're all so proud of everything you've achieved so far. And I know I've said this lots of times. Yeah, it was just really awesome. So just keep going, and we'll be working with you now to get your prototypes done for the end of the year and for your preliminary design review. But yeah, really well done. And it was just a great day for all of us. So the other really exciting thing that's happening is that August 3rd, we are scheduled to launch on CRS NG21, BinR 2, 3, and 4. So your teachers may have shared the link with you to the Eventbrite. Currently, it's 4 to 7 p.m. in Northbridge at the Piazza on Saturday, August 3rd, but that is highly subject to change because it's a rocket launch. So the time can move, the date can move. So if you do want to come, scan that QR code there to register for the event, and that way, if you have a family, anyone who wants to come along, it's a free event. But if you register there and you click, you subscribe to the updates, then we'll be able to get in touch with you really easily if the time changes, even like really close to the event. I think with BinR1, our launch got sort of moved 40 seconds out from launch. Probably won't be able to tell you that quickly, but yeah, hopefully we'll give you as much notice as possible for the final venue. But yes, please come along if you can, because BinR 234, this is us. This is the first time we've flown this version of the BinR CubeSat, and this is the version that your payloads are going to fly on when we get to the end of the program and build 5, 6, and 7. Hopefully, those are the ones you're going to go on, and you get to live stream the rocket launch from Cape Canaveral. SpaceX Falcon 9s are back up and running, so away we go. So first of all, what are electrical circuits? Electrical circuits are an everyday technology, from powering homes and appliances to enabling communication devices, medical equipment, and transportation systems. So effectively, they're everywhere. Our electrical circuits in particular, are small and are comprised of tiny connected components, enabling us to answer our science objectives. So there is a schematic from Altium, which is a software design program that you probably won't get stuck into just yet, of the BinRX Payload Development Program microcontroller boards that you're going to be sticking your payloads onto. And then in the top right there, that's actually a schematic of Will Blackie, who's the engineering support for BinRX. He graduated engineering last year, and he designed a horizon sensor payload as part of Dr. Robert Howie's tertiary course on spacecraft project, which is a course here at Curtin. He did a horizon sensor. You won't need to have anything quite that complicated. We're going to be using the more breadboard style payload boards, but you'll get to kind of get exposed to these really, really tiny components as well. But what we'll start with, if you're watching this on the video version as opposed to me delivering it in class, I'm not going to try and get you to go and we can't embed the YouTube video. So if you just scan that QR code if you're able to, or if you can't scan a QR code and you can't get onto YouTube, your teacher has the link to the YouTube video for how electricity works. So go and watch that, pause me, and come back here, and we'll keep going. All right. So block diagrams are not schematics. They're not complicated. It's basically a flow chart of your payload. So they are a visual representation of the components and flow of an electrical circuit or of any system, but we'll focus on your circuit and your payload design here. So rather than getting right into something called a schematic or something really, really complex, we're going to break down the system into subcomponents, which will make it easier to understand, design, troubleshoot, and communicate the system's functionality and relationship between components, as in, where is your sensor? What is your sensor talking to? Where's the data being sent? It's basically, it's a very, very simplified version of your payload. So when you're designing it, that blurred version there is the BinR 234 signals block diagram. So that's a lot more complex than the one you'll need to design, because that's the whole cube satellite, and that's on our side. It's blurred out just because it's top secret. But I want you to try creating your own. So you know from your mission concept review what your mission is, and you've done some requirements writing hopefully last week and had a chance to do that. And again, if you're stuck with anything, binrx@curtin.edu.au. If you're stuck, don't stay stuck, just reach out, we'll help. You want to start sketching out a block diagram for your project, showing all the critical components and how they interface with each other. You see there, just your microcontroller and your subsystem or your sensor, and the data flow goes back and forth, or which way does it go? So put lines in showing which way the data is going to go, the control, like is it a switch? Is it the BinR bus which is turning on and off? Have a look at your payload, the guide to your BinRx student payload, because that talks about how the BinR spacecraft controls your payload. But again, you don't need to know in detail. You'll just need to know, what what system is it that's switching your payload on. In this case, it's the BinR CubeSat Plus. So also show mechanical connections. So some of you might be doing reaction wheels, and with that have a mechanical component in there as well. So yes, put in lines showing data control and mechanical connections. You don't necessarily need to include power connections unless your block diagram is for a power system, which isn't really in this case. And then if you can use a pen and paper, you can use PowerPoint, you can use Illustrator or Draw.io. If you type that in, if you're able to access that on your school computers, that's a free online tool for creating flowcharts quickly and easily. So depending on how complex your payload is, the question is, have you oversimplified your payload? So do you need to amplify your sensor signal? Is a question you need to ask. So some sensors are low power, for example, so thermopiles or long wave infrared sensors, which I think some of you are using. They must be amplified to be read by the microcontrollers, something called an analog to digital converter, or ADC. So again, if you're not quite sure which, whether you need one or not, you can put it in as a question mark, or just sort of have a look into, what type of sensor you're thinking of using, and research if that needs to be amplified. And don't worry if you don't understand exactly how the amplification works. It's just, it's effectively, if you've got something that's not really producing really loud signals, you need to make them louder in, not necessarily in sound, but in voltage or whatever it is for the microcontroller to be able to pick it up, because sometimes it'll be such a low signal that the microcontrollers won't pick it up, and then you won't get any readings. So second question, what data does your sensor measure? So if you put an arrow entering the sensor block showing what is measured, for example, the thermopile would take in infrared waves. How does your sensor data get read? Does this sensor send the data to the microcontroller as an analog voltage? So that's when you see it as the curves on the data sheet, if you've started looking at data sheets, but we will go over data sheets another week. Or is it a digital signal, so on or off? Or even communication style. So that's probably further than you've gotten to just yet, but just to introduce you to the communication protocols in terms of how the data can be communicated in your payload. You can look into things like UART, I2C, or SPI, things like that. And yeah, do you have mechanical connections you're missing? So if your payload has a physical component, like a reaction wheel, do you need to include that as well? Sorry, we've jumped ahead. Did you overcomplicate? So do you show power signals? So if you look at the diagram here, that's probably it's a good example of one that's a little overcomplicated and not as tidy as it needs to be. So power signals are not required in this type of block diagram, as we only want to really see the flow of information and the transformations of the data, as in going from analog to digital, if that's happening. Did you break down your subsystems too much? So here, are they showing passive components like resistors or capacitors? Do they show the internals of the sensors? This is too much information for a block diagram. Save that for your more technical schematic diagrams. So in this case, there's some kind of sensor and they've included the lens. We don't need that. That's too much. Do you have too many connections? This can obscure the relationship between the components and prevent people from being able to understand your system or to troubleshoot it. So if you keep to the KISS, keep it simple, Stanley fundamentals, just enough information to understand what it is that your payload's doing. So if you're using inconsistent symbols or annotations, so stick to straight arrows and rectangles, as other notations may confuse people as they might not be as easily identified or understand the diagram's meaning. If you just keep it consistent, then the diagram is clear and universally interpretable. So that's what you should do. So just follow sort of very, very simple arrows, straight lines, rectangles. Simple as that. So introduction to schematic diagrams. We're going to watch, there's a video that's coming up that you can watch that talks about how to read a schematic, and it will go over these symbols as well. So on the left-hand side, you've got what you will see on a schematic drawing in terms of a simplified line drawing or symbol. And on the right-hand side, there's a little photo of what examples of those. So the first one we have are batteries. So you've got the battery. The first half of that little diagram is single cell and multi-cells. And then, just some common batteries. So I'm sure many of us are familiar with batteries. Resistors. The video say you've got the American symbol for resistors, the zigzag one, and the international symbol or the universal symbol is more just that rectangle. And then there's some resistors. So you've seen those from your kits. The ones with the little bands, and those bands do actually mean something. They're color-coded. If you're interested in learning how to read a resistor band, that's a fun party trick. And then those little ones, tiny ones next to it, those are surface mount components, which are basically the resistors. If you've ever had a look at our microcontroller boards, the ones that support your payloads, those are the miniaturized versions that you put on. And some of you have done pick and place where you kind of put them on with tweezers and then you bake them. It's quite fun. It's like making tiny Lego. Capacitors. The symbol for capacitor is the two straight lines, or a straight line and a curved line if it's polarized. So some are, some aren't. The video will get into that. And inductors, which are sort of coiled wire around a core. So that's there. And so we'll go to the video on the next page. If you are, and we've actually, got some more symbols. We've got our LEDs and diodes. So again, the video explains those. You've got the light emitting diode with the arrows, or just a regular diode. And then some images of those on the left. Op amps and integrated circuits. So op amps are things that amplify your signals, and integrated circuits, like that little one just in there. Ground. So again, that's important what the ground symbol looks like. More commonly, you see it as the three lines that's on the right there. Switches. You got a closed switch and an open switch, and then some examples of what a switch looks like. So those are all common schematic symbols. So now hop on over to the YouTube video on how to read a schematic, and that'll start to get you oriented on how to read a schematic. We don't need to do one this week, but next week we will actually be looking at that. So next week in BinRx is electronic concept design. So we'll take your block diagrams and start to make a schematic, start reading data sheets, learn how to start designing your payload using software, and then transferring to a solderless breadboard, just like the ones you've been using in the Introduction to Electronics kits. So yeah, thanks for listening and watching, and I will see you all soon. Take care. Bye.